Welcome everybody. I just wanted to start by saying I hope things are going well for you. I hope you're able to get in and find everything that you need. One of the things that I'm going to try to do at the beginning of most of these videos is keep you up to date on where to go to find new things. First off, let's talk about the announcement that I made that has information in it for this week. If you go to announcements and look at the week of March 23rd to March 27th, I have Monday's lecture video along with the lecture notes. We were in section 2.5 on Monday. We're going to be in section 2.6 of the text today. So you'll see this video pop up in just a second here on the video lecture screen. And then section 2.6 here has the topics, notes, some outside videos for you to watch. What I do want to point you to, though, is that I have been for the last, for starting, on Monday, uploading the textbook pages. So you can see here, if you left your textbook at home, this is the textbook page for section 2.6. You can take a look at that as well. So what I want to jump into with you today is a new topic for us, dealing with inhomogeneous PDEs. We've yet to really run into stuff like this. If you think about the way that most of our problems have gone, we've had U of t equal to k uxx for, say, the one-dimensional heat equation. And if it were a Dirichlet problem, then we would have the left end be 0, we would have the right end be 0. In other words, this is what we call a homogeneous boundary condition. However, what we're going to be dealing with today is the possibility that the boundary conditions are inhomogeneous. And so we're going to talk about how to handle partial differential equations that have inhomogeneous boundary conditions. And you're going to see that the technique we use is one that's reminiscent of some things we talked about in ODE, but at the end of the day, what you're going to see is this will lead to Friday's topic very well. So Friday's topic deals with the PDE being inhomogeneous versus the boundary condition being inhomogeneous. So this is an example that has homogeneous boundary conditions. Let me just show you what I mean by the difference between the two. So suppose I had the heat equation and I said, okay, let's let the left endpoint, maybe it varies between plus and minus 1 over time. And let's say the right endpoint is maybe the flow at the right endpoint is a constant number, but it's not 0. So you don't get no flow, but maybe it's, I don't know, minus 5. The units there would be degrees per, so it's with respect to x, degrees per, whatever our length units are. So degrees per meter per second. Degrees per second per meter. Oh no, because it would just be degrees per second. Sorry. So this is the flow rate at, say, the left endpoint, right? This would be an inhomogeneous set of boundary conditions, which we can solve using what we're going to talk about today. Contrast that with, say, a rod where you have some sort of internal heat generation. That's maybe it's increasing at a rate of 10 degrees internally. So this is an internal constant heat source. It's what we call a source term. If you have that and you still have the boundary conditions that are homogeneous, then this term makes the PDE inhomogeneous. So how do you solve if you have an inhomogeneous PDE? So far in the course, we've not been able to handle either of these, and the most important thing I want you to understand going into this is we've been using separation of variables so far. That only applies if the problem is linear, which everything we'll talk about in this course for the most part is linear, and homogeneous, meaning both boundary conditions and the PDE have to be homogeneous in order to use separation of variables. So what we're going to talk about today is how to change inhomogeneous conditions into homogeneous boundary conditions, but usually what ends up happening is usually by homogenizing, I know that's kind of a new word for you, usually by homogenizing boundary conditions, the PDE will become inhomogeneous. So what we're going to have to deal with then for Friday's lecture is I'm going to teach you how to take the problem on the left and turn it into the problem on the right. But then in Friday's lecture, we're going to learn how to solve the problem that shows up on the right. So how do we homogenize boundary conditions is today's topic. And then once we homogenize boundary conditions, how do we then solve the inhomogeneous PDE that results? Okay. Let's just look at a simple example to get us started with. I want to consider this inhomogeneous problem. So we've got the inhomogeneous boundary conditions here. The PDE itself is just the heat equation, so it is homogeneous. It is a Dirichlet problem because we're looking at the state, but it's not a homogeneous Dirichlet because they're not both zero. So the question that's asked is, what is the steady state solution for this equation? And I should mention what steady state means. So S of xt solves the problem for which u of xt, the limit as t goes to infinity of u of xt, occurs. In other words, we're thinking about the heat profile of this rod way far into the future after all the heat is redistributed and everything comes into this steady state formulation. What does that mean, though, to think about the limit as t goes to infinity of the solution to this problem? Well, it means that ut is approximately 0, utt is approximately 0. There's no change over time with respect to the u variable. And so if ut is approximately 0, then that means that the PDE is approximately given by this, which is really just this. So this is what's known as the steady state problem, or the steady state PDE, and its solution is what we call S of xt. So what I want you to do is, for this problem, pause the video here in just a second and try to solve this. What I want you to do is take a look and see, subject to these boundary conditions, if I'm solving this PDE, what's the solution for these boundary conditions? That'll be called the steady state PDE, or the steady state problem. All right? So if you haven't paused yet and tried to solve this yourself, you should do that. I'm going to talk about the solution now. So if u of x equals 0, we know we could take the integral of both sides with respect to x once. We know on the right-hand side that would be ux equals, on the right-hand side, it's going to be integral of 0, 0 plus a constant. That constant is with respect to x. It's constant with respect to x. So it would be an arbitrary function of time. And then if I was to do this one more time, what you would see is you get this times x plus another constant, which is b of t. We did some problems like this earlier in the course, but the point is, this is the steady state profile. It varies linearly across the rod, which makes a ton of sense. I'll look at the geometry of that here in just a second. But if we look at the boundary conditions here, the boundary condition at the left endpoint is K1. The boundary condition at the right endpoint is K2. So starting with the left endpoint, if I apply x equal to 0, I get a times 0 plus b is K1. So b is K1. And if I apply it at the right endpoint, where x is L, I get a times L plus K1, because b is K1, is equal to K2. So a is K2 minus K1 divided by L. So overall, my steady state problem is the solution to this problem, or my steady state is the solution to this problem. and it's given to us by k2 minus k1 over L times x plus b1 is k1. So this is the steady state. Now what I'm going to do is compare that with the answers above, and it looks like number 3 is correct. So hopefully you're able to find number 3. Essentially all I'm doing when I'm solving for the steady state problem is I'm taking any of the derivatives with respect to time and I'm making them 0, and I'm solving the ODE that results from that. So that's the steady state solution. So what do I do with this steady state solution, and why is it so important? Let me talk about the rod here for just 1 second before I get into that, just so you can understand why this makes so much sense. So, why does this make sense? Well, you've got a rod, and at t equal to infinity, so at t go to infinity, what does the solution u of xt versus x look like? Well, the rod, so imagine the rod's kind of here. And so this would be at L. And so the graph that I'm going to put above this is what the graph of the temperature would look like after everything has redistributed itself. Well, suppose at the left end we're at the point 0, K1. Because the temperature at the left end is K1. And suppose at the right end we're at the point LK2. We don't move off those points, so we start with the temperature being K1 and K2 at time equal to 0, and they're held at that temperature for all time. So eventually, whatever was going on in between these things, whatever the temperature profile was initially between these things, what'll happen is if it's much higher over here, it'll drop, and if it's much lower over here, it'll raise because of the heat being supplied here. So what you will get is you will get a linear variation. You'll get a linear variation in the heat over time. That should make a ton of sense. So this is what the long-term steady state profile is going to be. This is your steady state solution. It's equal to, you have 2 points, so you can find the equation of a line through 2 points. The slope of that line would be k2 minus k1 over L minus 0 times x plus the y-intercept is k1. You can see that is exactly the same as the steady state we got by solving the PDE. So if you have fixed conditions at the left and right, then you'll get a linear variation over the length of the rod in temperature going from K1 to, say, K2. That should make a ton of sense physically. Now the question is, I still want to solve this PDE. We haven't solved the PDE yet. I've just told you what it looks like as time goes to infinity. I need to know what it looks like for all time, not just time at infinity. Well, here's where the niceness of this method comes into play. So if I want the full solution to this problem, u of xt, I'm going to assume, is the part at infinity plus the transient part that leads up to the steady state. So this is what we call the steady state solution. And this is what we call the transient solution. And if you remember from our theory of linear differential equations in ODE, every solution to a linear differential equation has a steady state part and a transient part. The same is true of linear partial differential equations. And here's how we're going to use this. We're going to substitute into the actual initial boundary value problem that we were given. So the initial boundary value problem is given by this, and we're going to substitute in our new u and figure out what every piece of this turns into. So we'll start with a reminder of what S of xt is. And now look at the substitution. So substituting in ut would be s with respect to t plus w with respect to t. But s with respect to t, this does not depend on time at all. So s with respect to t is 0. So ut is just w of t. So here I'm going to start transforming this. So ut is just w of t. What is uxx? Well, if you look at the steady state solution with respect to x, it's linear with respect to x, so two derivatives of this would be 0. Well, it would be sxx plus wxx. And two derivatives of s with respect to x would be 0, leaving you with just wxx. So uxx is wxx. So the PDE hasn't changed at all. The PDE for the entire solution is the same as the PDE for the transient solution. What about the boundary conditions? So u of 0t would be s of 0t plus w of 0t. S of 0t, so if I make x equal to 0, if I make x equal to 0 in this condition, then that leaves s of 0t is equal to k1. But u of 0t is k1, so u of 0t is k1. You see you've got k1 on both sides. Those cancel, which means w of 0t is just 0. So we've managed to homogenize the left end. The left end was inhomogeneous previously. It is now homogeneous in terms of the w solution. Similarly, if I look at w of lt, which is s of lt plus w of lt, then s of lt, if I make x equal to L, you can see the L's would cancel, minus k1 plus k1 cancel, leaving you with just k2. And here, once again, you can see you've got k2 on both sides, so this gives w of lt equals 0. So we've managed to homogenize both of the boundary conditions. Let's see about the initial condition. The initial condition, u of x0 equals phi of x. So that's equal to s of x0 plus w of x0. We're not going to get off quite as easy here. If I make t equal to 0 in s, nothing changes because there are no functions of t here. So setting t equal to 0 in this doesn't make any difference at all. So this is going to be k2 minus k1 over L times x plus k1 plus w of x0. All of that is equal to phi of x. So this tells me that w of x0 is phi of x. I've got to subtract all of this over minus, I'm just going to write it for now as s of x0. But we know that that is this term. So this is my new PDE to solve. So this is the new PDE that'll allow me to solve for W. So think about what we've done. We've assumed that U was a steady state plus a transient. We solved for the steady state. We found the new PDE to solve for the transient. And the nice thing is this is a PDE we already know the solution of. This is a heat equation with Dirichlet conditions on both ends. It just has a weird looking initial condition, but that's not a difficulty for us. We know that W of xt is the sum and goes from 1 to infinity of Bn times, we've got the time problem, so n pi over L are our eigenvalues. So there's our time problem. We know since it's Dirichlet, the eigenfunctions are sine. So there's our general solution to this problem. The boundary conditions would the coefficients are found via the initial condition. We know normally it would be 2 over L integral from 0 to L of whatever the initial condition is times the eigenfunctions. But here our initial condition is given to us by phi of x minus k2 minus k1 over L times x plus k1 dx. Whoops, forgot my eigenfunction. Sine n pi x over L dx. x. So this is going to give me all of the coefficients, so now I have a particular solution. So this is a known problem. In other words, we homogenized the original problem into a known PDE that we have used separation of variables on. If you notice, I can use separation of variables on this problem because the resulting PDE was homogeneous and the resulting boundary conditions are homogeneous. Just had a weird initial condition. So this problem is solved. I have the solution at this point. However, what was unique about this problem and is going to change with the next example is the boundary conditions that we started with here don't depend on time. They don't vary over time, which means when we took right here the partial of s with respect to t, it vanished because our boundary conditions didn't depend on time. But if our boundary conditions do depend on time, this term will not vanish, and you're going to see that in the next example. So here we have a slightly different problem. We have once again, this is a heat equation. I could do this with the wave equation as well. It's just for the wave equation, finding the steady state's a little bit different, but you could still do it. The boundary conditions here are Dirichlet at the left endpoint, so we have a state that evolves over time at the left endpoint, and then you have a mixed Robin condition here at the right endpoint, and you've got some initial temperature profile. So we're going to change this to a problem with homogeneous boundary conditions. What do you think will happen here? Well, I kind of gave it away there just a second ago. We're going to end up with an inhomogeneous PDE to solve, and we're going to do that on Friday. But that's what's going to happen here. So the steady state, so S of xt solves u of xx equal to 0. Once again, remember, with respect to time, u is 0 because you're looking at it time has gone on to infinity. So u is no longer changing over time. So solves this. We just did this, so we know that S of xt is a of t times x plus, let's say, b of t. I want to apply the initial conditions. So I'll start with u of 0t equal g1 of t. So I've got to satisfy S of 0t, which would be a of t times 0 plus b of t. That must equal g1, which implies that b is g1. And then the other condition is Sx at L plus h S at L equals g2. So I'm taking the partial of this with respect to x first. That gives me just a of t. Plus h times this thing all over again, where x is now L. So I want to solve for a. So I'm going to stop writing of t. We know these are functions of t. So this is going to be a 1 plus hl plus hb, but b is g1, so I'm going to write g1 here, equals g2. And so a is g2 minus g1h over 1 plus hl. So my steady state for this problem is g2 minus g1h over 1 plus hl times x plus, let's see, b of t here is g2 of t. No, g1 of t, excuse me, g1 of t. All right, so there is my steady state for this problem. Once again, it's a linear variation in x, but it is not constant with respect to time because g2, g1, those are all functions of time. So this is truly a function of both position and time. Now that I've determined that, what I would like to do is plug it back into the original problem, see what happens to the transient problem. So I'm going to do a little bit of my scratch work here to get started with that. Actually, I think it'll just be easier if I bring this down. So I'm going to bring this down. So there's my steady state problem. And then I'm going to substitute u equal to s plus w into this. So we know ut is st plus w with respect to t. But this with respect to t is actually rather difficult to find because g2, g1, g1, those are all functions of time. So I would have to take their derivatives with respect to t. I don't know what they are with respect to t, but I could find each one of those. So the point is, this is not equal to 0. So even though this thing is, it's not, when I plug this in, I can't get rid of any pieces is what I'm trying to say. So I've got to leave this just as s of t plus w of t. uxx, on the other hand, I can do something about. This is still linear with respect to x, so if I take two derivatives of this with respect to x, it all disappears. So what is the new PDE going to look like? Well, ut is st plus wt. uxx is 0. 0 plus wx, so it would be sxx plus wxx, which would be 0 plus w of xx. So this would be 0 plus wxx. So our new PDE is the heat equation, but this term gets subtracted over. I now have a source. I now have a part of the problem that's giving me some sort of internal heat generation over time for the transient problem, or at least it's acting like that. So this is the new PDE to solve. It's not like the old problem. And we could write down st if we wanted to, right? It's just g2 prime minus g1 prime h. These are all linear. There's no product rule or anything like that going on here. So we know what this looks like. It's just, I don't want to mess things up by plugging this awful looking thing in there. So that's that term right there. So we've got our new PDE, but I want to look and verify that we do have homogeneous boundary conditions because we are going to here. So let's quickly take a look at that. The boundary conditions here were u of 0t equal g1 of t. So let's start there. This is u of 0t is s of 0t plus w of 0t equals g1. So here's s. If you make x equal to 0, if you make x equal to 0 here, you just get g1. So this is easy enough. W of 0t is just going to be 0. So there's our first boundary condition for w. The next one's not quite as easy. It's u sub x of lt plus h u of lt equals g2. So this would be sx plus hsl equal or plus wxlt plus hwlt equals g2. What I have to show is I have to show this is equal to g2 so it'll cancel out. And that's it's going to take a little bit of effort here. So let's look at each piece of it. Let's start with s with respect to x. So s with respect to x, you can see I've got s of xt here. If I take the partial with respect to x, the g1 goes away because it's a function of t. X goes away, you just get this slope term. And we're going to come back here in a second and do something with that term, but I'll just leave it like this for now. And then the other part of this is you've got h times s of lt. So if I take the steady state problem right here, and I make x equal to L and multiply it all through by h, you get g2 minus g1h over 1 plus hl. X is now L, but you've multiplied through by h. G1 gets multiplied by h as well. So these are the terms that you have. And what we would like to do at this point is show that if you add these two terms, we'd like to show that that's G2. So here you've got G2 over 1 plus HL minus G1H over 1 plus HL. This one is G2 LH over 1 plus HL minus G1LH squared over 1 plus HL. And you see here how all of the terms are over 1 plus HL. I'm going to get a common denominator for this term. And what we'd like to see is all this stuff cancel, leaving us with a G2. And in fact, it does cancel. Let me show you. Here I have a G2LH. Oh, I forgot that up here. So this sorry, I should have made X. No, I think we're good. Okay. So you've got the G1H minus G1H. You've got a plus G1H here, right? So minus G1H plus G1H. You've got a minus G1LH squared. Here you've got H times H is H squared, so that's LH squared. That term cancels with that term. And then you've got these two G2 terms left. So remember, we're adding these, right? We're adding these two things together. So we're taking this plus this. So this gives you G2 1 plus HL plus G2 LH over 1 plus HL. And what you can see is when you get a common denominator, factor out that G2 there, 1 plus LH over 1 plus HL, those terms cancel, leaving you with just G2. So you do in fact get this thing to be G2, which means that it cancels with the right-hand side, which leaves you the other boundary condition being homogenized as well. And so that term is now 0 also. All right, so putting these all together, we've got our new PDE. We now have homogenized boundary conditions. This is a Robin problem, which we know how to solve. This is Dirichlet at the left end. We know how to solve this kind of boundary condition. We just don't know how to solve this kind of PDE. And we'd also need to look at the initial condition. So the initial condition here was u of x 0 equal phi of x, or excuse me, f of x here. So that would say that s of x 0 plus w of x 0 would be equal to f of x, or my new initial condition would be w of x0 is f of x minus s of x0. So our new problem, we know what our new initial boundary value problem is, right? It contains, to show you all of these at one time, it contains this new PDE, which is inhomogeneous. We've homogenized the boundary conditions at least, so we've made some progress. And we've got this as our new initial condition. So in order to solve this transient problem and solve the entire problem that we were looking at, I'm going to have to be able to solve an inhomogeneous PDE. And that's what Friday is going to be about. Friday, we're going to take a look at how to solve PDEs of this type. So this is a little bit of a shorter video today. There's a lot to sort of digest here. I suggest you read through section 2.6 and make sure that you understand this material. This is the material that's going to be on your quiz at the end of the week. You're going to have to be able to do this exact thing, and that is find the steady state for a given problem and do the steady state transient substitution to homogenize the boundary conditions. All right, I'll see you back here on Friday with another lecture, and I hope everyone's doing well. Talk to you later.